Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ridwan bin Azman from Group 5, and today I will explain about the truss design and analysis for communication towers. And our lecturer name is Dr. Ashraf Izwan bin Hamdan. Okay, these our group members. First is myself is Muhammad Ramil Azman. Second, Nur Ashida binti Muhammad Sharifuddin. Third, Muhammad Arish Razin bin Ali Bakar. Fourth, Muhammad Afiq Syami bin Sari, and the last one is Putri Nurul Azhar Fatihah binti Awaluddin. Okay, for introduction, in today's digital age, communication towers are essential for service like mobile networks, TV or radio broadcasting, internet access, and military communications. These towers must be tall, strong, and lightweight, capable of withstanding wind, earthquakes, and temperature change. Why use trusses? Trusses are made of interconnected straight members forming triangle. This design provides high strength and with minimal material, making them ideal for supporting vertical and lateral loads. Among various types, the electric truss is widely used in towers due to its strength, stability, and efficiency. Okay, for key design considerations, first, it supports vertical loads such as antennas and so on. Next, it resists lateral force such as wind, seismic, like shaking. Okay, next is it's easy to fabricate and assemble. And the last one is cost effective with safe material use. So, the most towers have 3 or 4 leg base to improve stability and load distribution. The electric truss is preferred for its ability to handle forces from all directions and is built to redundancy, making it available for tall structure. Okay, this is the description of electric truss. Electric truss in communication towers. First, criss-cross diagonal design form strong triangle for even load distribution. Is built in triangular or square vertical section to resist vertical, such as antenna or tower weight, and lateral, such as wind and seismic force. Next, multiple loads path increase safety if damaged. Next is modular and prefabricated, easy to assemble on site, ideal for remote areas. Next is open design allows easy installation of antennas and cables. Okay, the last one is common in towers 15 to 100 plus meter tall, used in both self-supporting towers and guide masts. Okay, now I will explain about the justification for electric truss that the tower we use for our project. Okay, why the electric truss was chosen? First, is proven in real-world towers for height stability and wind resistance. Next, electric truss balance material efficiency with structural strength. Electric truss also suitable for 50-meter height and various load condition. And it also offer redundancy, load distribution, and strong structural integrity. The last one is electric truss follows industry standard and provide a great learning experience in tower mechanics.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afiq Syami bin Sari, nombor matrik CN240394. And for my part is literature review. So, communication towers rely on efficient designs to balance strength and functionality. Lattice trusses like those in the Eiffel Tower are a standout example. Their open web, triangulated structure distribute loads effectively while minimizing material use. Engineers often choose between Warren or Pratt configurations. Warren trusses excel in strength for tall towers, while Pratt trusses simplify maintenance. However, lattice trusses faces challenges. As build-up can increase wind load by 300%, and their open design requires 15 to 25% more maintenance than monopoles. Thankfully, innovations like lightweight composite materials, adaptive bracing for high winds, and drone-assisted inspection are addressing these issues. Let's compare the three main tower types. First, lattice trusses dominate in height, exceeding 2,000 feet and wind resistance, but they are costly to assemble and maintain. Second, monopoles, ideal for cities, max out at 300 feet but shed ice well and need least upkeep. Third, Guyet mast, budget friendly for extreme heights but rely on cables that ice up and require land. The takeaway, lattice trusses suit heavy duty applications, monopoles fit urban spaces, and Guyet must work for rural or temporary setups. For case study, a great example of innovation is the Wills Towers 2018 upgrade. To support 5G, engineers replaced steel with carbon fiber, cutting weight by 18%. They added hexagonal sub-lattices for antennas and used modular components, speeding up installation by 27%. This project shows how lattice trusses can evolve to meet modern demands. Not all adaptations succeed. The 2016 Wyoming tower collapse revealed critical flaws. That is, 60% of bolts had undetected cracks, and new 5G antennas caused vibrations beyond the original design. This disaster prompted stricter rules. Today, all retrofits must pass harmonic load tests to prevent resonance failures. The future is exciting. Imagine 4D printed lattices that self-assemble, quantum dot coatings that visualize stress, or even orbital communication towers. Hybrid system that is like lattice monopole combos will likely dominate, merging the strength of lattices with monopoles low maintenance. So in summary, lattice trusses are tall and strong but need care. Monopoles can save space in cities, and Guyet masts are cost effective but land hungry.
Assalamualaikum. It's between November and December CN 3047. I want to talk about theory communication tower trusses. When design communication tower trusses, engineers use principle of balance and stability. A truss is stable when all force and moments acting on it add up to zero. Trusses are made of straight bars joined at points and carry loads using tension and compression. To make calculation easier, connections are assumed to be frictionless links. Two common methods used to find faults in truss members are method of joints analysis, each joint one by one. Second method of section cuts the truss to look at specific parts. Okay, next I will talk about design a truss tower involves several components that to make sure it is strong, stable, and works well. Below is a basic outline of how engineers design a truss tower. First, requirement analysis. In requirement analysis, have load assessment. Load assessment find out all loads the tower will carry, like maintenance, wind, and weather. Next, height and span. Decide how tall and wide the tower should be. Last, material choice. Pick strong and durable materials, usually steel or aluminum. Okay, next. The second is conceptual design. Conceptual design have truss layout. Choose a truss shape and suit the purpose. Next, joint design. Plan strong connection using bolts, welding, or automatic. Third, structural analysis. Structural analysis have load response. Check how the tower handles different force, nets, stress, and deflection. Make sure the structure won't bend or break under pressure. Lastly, the mechanism design. Communication tower truss is detailed design and optimization. Detailed design optimization have component design. Draw and specify all parts of the tower. Next, optimization. Adjust the design to save materials and cost without reducing safety.
Hello, my name is Nur Ashida binti Muhammad Saifuddin. My metric number is CN240231. Today I will present a design electric truss tower. So the left side is the sketching drawing from our group that designed the tower. Next to it, 2D diagram. We are using AutoCAD software to scratch it to make it 2D diagram, because 2D diagram represent object or a concept in a two-dimensional, typically on a flat surface such as a piece of paper or a computer screen. Then it use length and width to detect object but lack depth. So next to it, the middle one is a 3D diagram. Same, we are using software AutoCAD. So the 3D diagram is a visual representation of an object or space that include three dimension is length, width, depth. This allow for the more realistic and comprehensive view compared to 2D drawing. Enable rotation and exploration from various angles. So the right side is a free body diagram. Same, we are using software AutoCAD. So a free body diagram is a simple drawing that show all the forces acting on an object, and it used in a physics and engineering to analyze force and moment on bodies to simplify complex situations for easy analysis. Essentially, it is a visual representation of the force acting on an object, allowing you to isolate the object and understand the behavior. Okay, next we present the calculation lattice truss tower. Firstly, we find the external force. So total of the external force, we can get the 210 Newton. Next, I will find the reaction at A and B. A and B is a pin connection. So at the summation of Fx, we can get the Fax plus Fbx equal to 0. So next, at the summation of Fy equal to 0, we can get the Fay and Fby equal to 210 Newton. Fay and plus Fay and Fbx unknown. So we can get the Fby from the momentum equal to 0. Summation of momentum is 0. So at the momentum, we can get the Fby equal to 150 Newton. So we put in this equation Fay plus Fby, we can get the Fay equal to 60 Newton. Okay, next we find the force at each joint. So joint A, at the summation of Fy, we can get the Fay plus Fac sin 32 Newton. We can get the Fac equal to negative 113.2 Newton. At the summation of Fx, we can get the Fad plus Fac cos 32 equal to 0. We can get the Fad equal to 96 Newton. Next, at the joint B, summation of Fy equal to 0. we can get the FBC sin 34 plus FBY. So we can get the FBC equal to negative 268 Newton. At the summation of Fx, we can get the FBD plus FBC cos 34 degrees. We can get the FBD equal to 222.2 Newton. Next, at a joint C, we can get the FCD equal to 560.3 Newton. At the summation of Fx, we can get the FCE equal to 153.5 Newton. At the joint D, summation of Fy, we can get the FDF equal to negative 287 Newton. And summation of Fx at the joint D, we can get the FDE equal to negative 594.2 Newton.
Okay, good morning. My name is Muhammad Arif Razin bin Ali Akbar. My matrix number is CN240433. Okay, today I'm going to talk about the discussion of this project. Okay, the use of lattice truss structures in communication tower design is highly advantageous due to their efficiency in distributing the loads. It also has an advantage of resisting environmental forces such as the wind. The wind plays a huge role because the communication tower is built tall. Okay, the lattice truss is built using steel arranged in triangular units, offering high strength to weight ratio, which is ideal for tall communication towers, such as I said before. Okay, the key factors considered in this analysis include material selection steel due to high strength, because most of the communication tower is built using steel. So lattice truss also uses steel arranged in triangular units, such as I said before. Okay, another key factor is member forces, such as the joint method is used to analyze the force to ensure stability. The support condition is also one of the key factors, because the base and foundation designed to resist overturning moments and horizontal shear. Okay, in analysis tool such as joint method are used. Geometry of truss height, base width, and spacing of nodes also affect overall deflection under the load. Okay, that's it from me. Thank you.
Okay, in conclusion, the design and analysis of a communication tower using a lattice truss system demonstrates the effectiveness of this structural form in achieving high strength and stability with minimal material usage. Lattice trusses offers excellent load carrying capabilities while being economically and relatively easy to fabricate and erect. Proper analysis ensures the tower's performance under all expected loading conditions, making it a reliable solution for modern telecommunication infrastructure. To ensure success, engineers must integrate careful load analysis, member sizing, and consideration of dynamic forces like wind. The study validates that lattice truss towers remain a vital design choice for high-rise communication structures due to their resilience, efficiency, and adaptability. Okay, thank you.